Lecture today. In the last lecture, we talked about general function approximation. Where we're at the most difficult contents of the reinforcement of this class. So we have talking about the basic algorithm fit equation, which is something like a function approximation version of value iteration. And we have talked about the offline guarantees, where if we have the all policy controllability, what kind of guarantees we can have for fit equation, which is similar to the in the offline setting, what kind of guarantee we can have for the value iteration. Then we switch to talk about the online setting. We say in the offline setting, one thing we require is we need to look at the log cardinality of the function class, which kind of like describe the complexity of this like offline reinforcement learning, like how complex it is to learn from generic function class. But in the online learning, online reinforcement learning, we actually require one more complexity measure. We're introduced in the end that's called Bellman rank. So we first recap what is the Bellman rank. In order to introduce the Bellman rank, we first need to define the average Bellman error. With rho in policy. So the definition is quite straightforward. It says for any function, value function in this function class f, and for any policy pi, we can define this average Bellman arrow using at step h, looking at value function f and rho in policy pi is defined as we take an expectation where in the first h minus 1 step, we use policy pi, 1 to h minus 1, and in the very last step, at h step, we use the policy f. So in the earlier, like in a 1 to h minus 1 step, we use this policy, rho in policy pi. Well, in the h step, we use the greedy policy of this f to take the action. And then we look at the Bellman arrow as the name. So Bellman arrow look at the value of the current step and look at the difference of this value to if we apply the Bellman operator on the value of the next step. Okay. And we say this is a key quantity of the Bellman rank. Bellman rank essentially is just look at this average Bellman arrow and say how complex this Bellman arrow can be. Let this epsilon h be the matrix in R f by f. Essentially, we look at a matrix spanned by this average Bellman arrow quantity. In a sense, we look at the following, whose f prime entries. So this is a matrix of you have a cardinality of f rows and cardinality of f columns, and where each entry is indexed by a function, and this f prime entry is just this average Bellman arrow with evaluated on this value function f with rho in policy pi f prime. So you can think it's essentially just expanding this Bellman arrow, but apply it to all the values in my function class and all the greedy policies in my function class. Okay, so and span to get an entire matrix. So this matrix kind of like describes how complex your function value can be. So we define the Bellman rank. Of an MDPM with function class F. Is defined as essentially the rank of this matrix. Let's say Bellman rank. Okay, so we look at the rank of this matrix at every step. And we essentially take the max over this rank, and this is defined as a Bellman rank. So you can think as, again, like we look at a very natural quantity that is Bellman, average Bellman arrow, which have a rowing policy, and also the value, which we look at the arrow. And then Bellman rank is essentially just the rank if we look at the matrix whose entry is this Bellman arrow. So one very important thing we notice is this is like rank is defined as in terms of like this matrix, but in order to prove for example, Bellman rank is less than D, all we need to show is there exists some map which maps function to d-dimensional space. So that for any ff prime and any h, you can essentially define this for a different h. Let's say for any h, there exists some maps so that for any ff prime, what we have is this average Bellman arrow defined on this f, and pi f prime can be decomposed as the inner product of c f and zeta f prime. Once we can show this, you can essentially think we're decomposing this in this c matrix, this epsilon matrix, epsilon h, to be like a lot of row vectors and column vectors, which are denoted by this c and zeta. So this is one of the sufficient conditions to show the Bellman rank is less than D, because what you're saying is if this entire matrix can be factorized by inner product of two d-dimensional vector, this essentially says the rank is at most D. And we will actually use this characteristic to prove a lot of MDP or a lot of reinforcement learning problem we have considered so far is actually has like low Bellman rank, so that we're not like inventing some new things and And actually, a lot of previous stuff can follow in this generic framework. Okay, so any questions about the definition of the Bellman rank? I guess we have talked about most of them in the last lecture, and this is mostly just a recap. If no questions, we will talk about some examples. So proposition 1 says we look at the tabular MDP. We're seeing tabular MDP following this class that has a low rank, a low Bellman rank. So we say let function class be all the possible value functions. So in the tabular case, we don't need to do any function approximation. So this F just the entire value function class. For the tabular MDP, then we can show the Bellman rank. Is less or equal to S, where S is the number of states. And because in the tabular setting, we know S is finite and small, so this is completely fine. Okay. So we'll show why this is true. So basically, we just use these characteristics this way to show this true. And we look at this average Bellman arrow, where we evaluate at a function f, value function f, with rolling policy pi f prime. So we know by definition, this is the expected value of Bellman arrow, which Bellman arrow take this form. So what we can do is we can explicitly write out the Bellman arrow, explicitly write out the expectation part. So we will take expectation over the state sh, like with summation over the state sh. So the first part is we have the probability until h steps. We know rolling policy, we follow the policy pi f prime. So we look at what is the probability we're going to visit sh if I use the policy pi f prime till h step. Then we need to take expectation. So this expectation need to take expectation over both sh and ah. So we have written the sh part. For the ah part, we say ah is sampled from pi f dot sh. Okay. So this ah is sampled from the greedy policy and the condition on sh. And then we just copy the Bellman arrow part. fh, sh, ah, subtract the Bellman operator, operates on the next value. So what's important? This is pretty straightforward. This essentially is an inner product form. Okay, so inner product is we kind of like summation over index. This is a summation over the index. Index is like the state. What is the state is the index, and you can think this thing is is a coordinate of S-dimensional vector. This thing, again, is also a coordinate of S-dimensional vector as well. And this is essentially summation over the coordinate. So we know this essentially already following the form of this Xi f and zeta f prime, where you can write out the map where this Xh is defined by this probability of this f prime, of this f. So this zeta is defined in terms of this probability, where we're only taking, with the rolling policy, pi f prime, and the second part is only about f. Yeah. And I think the most important thing is the first component only depends on f prime. And the second component only depends on f. So this decomposition already achieved what we want in a Bellman rank. And this essentially says the dimensionality is S. This inner product is S-dimensional. Any questions about this part so far? Okay, so if you are cool with this tabular MDP being like has a low Bellman rank, we can also look at the second example where we look at one example beyond the tabular case that is a linear bandit. A linear MDP. We can also say this class is a special case where it has a low Bellman rank. So we say the Bellman rank sorry, of linear MDP is less or equal to dimensionality. Where we again do the similar decomposition. We look at the average Bellman arrow, f and pi f prime. And we look at we expand out the expectation in the definition. So what we have here is, again, we look at the expectation of SH sampled from pi f prime, which is a rolling policy, and action AH sampled from the greedy policy, pi f, condition on SH. And this Bellman arrow. And for the Bellman arrow, we just, for simplicity, denote it as delta H, F, SH, AH. This is just simplicity. This is just a Bellman arrow. Okay, I kind of like this, just exactly the notation as F minus TH, FH plus 1. I just denote it as a delta to avoid like repeatedly written a lot of like a Bellman arrow, a Bellman operator, and a bunch of things. So now what we need to do is we need to expand out what is this expectation. Okay. So what we can do is we understand for the linear MDP, one thing we can leverage is the transition is linear. So we can look at one step earlier, that is sh minus 1, ah minus 1. We know this thing is, again, sampled from the policy pi f prime. This is like a rolling policy. And we look at the very last step, sh. We understand the probability, transition probability follows the linear structure. So this is something like phi, sh minus 1, ah minus 1, and the inner product with the probability measure on sh. Okay. And this measure need to inner product with this expectation of ah sampled from pi f sh and delta h f sh ah sh. Okay, I'm just copying whatever on the top. So this is by definition of we're using the linear transition. So the transition looks at the feature vector of h minus 1 step, that is sh minus 1, ah minus 1, and the inner product with like a vector version of measure, d mu, and then d mu need to product whatever is left there. So the important thing here is we notice this expectation is only on sh minus 1, ah minus 1. But the right expression, actually, everything depends only on the sh, is independent of sh minus 1 and ah minus 1. So that means we can move this expectation inside to only operate on the left term. So this is equal to the expectation of sh minus 1, ah minus 1, sample from pi f prime. And phi sh minus 1, ah minus 1. On right hand side, we just still copy everything. Okay, this delta h f sh ah given sh. Now we again goes to this form where this left side of the inner product only depends on f prime, where on the right hand side of the inner product only depends on f. So we again achieve this kind of decomposition between these two things. So this is just equal to some c of f inner product with zeta f prime, where this c and zeta is defined here and here. Okay, this specific construction, and where the dimensionality is this is like a d-dimension inner product. So finally, I also want to say, now we see like Bellman rank kind of like subsume the both tabular case and linear case, but it also includes a bunch of like new setting that is not in either like tabular or linear. For example, we can also look at one example called block MDP. So block MDP is should be considered as like an easy case of partially observable MDP or something. I think it should not be partially observable, but I think following the partially observable MDP model, so we should look at the, so underlying it's an MDP, for example, S1, S2 to S3, and we also have an action, A1, A2 at a time, and where A2, S1 will jointly affect S2, and A2, S2 will jointly affect S3. So everything at the bottom layer is basically the same as MDP. So what's different is this is like unobserved. The state is unobserved. But we have observed some observation that is generated from S1, S2, S3. This is observed. So this is like a general model of a partially observable MDP, where we don't observe the underlying states, but we observe some observation that is generated from the states. So what is special about this block MDP is a block MDP will assume there exists a decoder so that, let's call decoder phi star h. So we have one decoder at every step, so that the underlying states can be decoded as a function of the observation at each step for every edge. So you should consider this as more or less some like a rich observation scenario where we still have an underlying MDP, but we observe probably it's like an image representation of this underlying MDP. So that the observation is like in some very rich space. For example, I'm just doing a robotics manipulation or like some car driving on the road, where the underlying representation states is like very small. It only like is a position and the velocity of the car. But my observation can be very rich. I'm observing the entire image, which has background, has lightning, has a lot of other effects. So the decoder essentially is removing all the redundant information and only look at the states. So this block MDP has a very important thing that is essentially all observation. It should not, I'm saying it's following the partially observable MDP like framework, but it should not be considered partially observable because this observation can like have the complete information about the states and actually have some actual information about the states we want to get rid of. So the good thing about this is it's sufficient to consider the function class, the value function class. That f basically only look at the current observation and action and maps it to a real value. So you can think this observation as will serve as a more complex states. Okay, so this coordinate of O can be infinite. Well, this S is small. This is like the basic assumption we make. So we're saying the underlying possible states, underlying degree of freedom of movement is like small. Well, because we're observing image, so the complexity of this observation is like very, very large. So if we're naively applying some tabular results, we're going to pay the cardinality of observation, which is like not acceptable. So this is why we need to use this general function approximation framework and look at the Bellman rank. So it turns out for Bellman rank, you can also do the similar decomposition, where we look at the average error of this f and pi f prime. This, by definition, is again equal to we roll in policy with pi f prime at 1 to h minus 1 step and pi f at h step. And we look at the Bellman arrow. Well, now the Bellman arrow will be a function of OH and AH, because we're essentially using O to serve as our states, and subtract by the Bellman operator on the function of h plus 1 step and OH, AH. Okay. Although now the entire function is on O, it doesn't hurt us to essentially take an expectation first over SH, and then we take expectation conditional on SH on OH and AH. So what are we going to do here is we first look at, we can essentially express this expectation, a summation over SH, and the probability of taking a rolling policy pi f prime of visiting SH step. And the remaining stuff actually not only depends on AH, but also depends on OH, where OH is generated from the SH. So the remaining thing now is the expectation of AH, sample from this policy. Okay, first is OH, generated from SH. This is like emission probability. It's a probability conditional on SH. What is the probability going to generate some observation? And then the AH is going to generate it from some policy that depends on OH. Okay, finally copy the Bellman arrow. So now we again see this becomes an inner product between something like S dimension and S dimension. Well, the first part only depends on F prime, and the second part only on the F. So this again is equal to CF and zeta F prime, where this is like a S dimensional. So what do we have achieved here? So we look at the block MDP. Essentially, it's an augmented version of original MDP, but now we have like a more complex, very rich observation. So very complex observation. And if we just use the original tabular guarantees, we're going to pay this cardinality of O, which is huge. It's like very, very large, tremendous. But basically, if we're using the Bellman rank framework, we actually can look at the complexity measure of this function class measured by Bellman rank, and we actually see the Bellman rank is actually not that large. Bellman rank is just the underlying number of states instead of the total cardinality of observation. So this gives a significant improvement. So there are a lot other more examples. You can show the Bellman rank is small. So the next question you may have is, okay, now I know for a lot of examples the Bellman rank is small. Then what are we going to do with this Bellman rank is small? Like, what is the algorithm that can leverage the small Bellman rank to still give the efficient guarantees? It turns out the algorithm is actually also a very natural algorithm. So we're going to introduce the next thing is we're going to have an algorithm that can leverage this small Bellman rank and to provide an efficient guarantee to find an optimal policy. So the algorithm is called GORF algorithm. GORF stands for Global Optimism based on local fitting. So by the name, you can actually know we actually exploited the mechanism called global optimism. So it is in our language of this class. So basically an algorithm which combines both fitted Q iteration, which is the algorithm we use for the generic function approximation, with the global optimism. So the algorithm was introduced in the paper of Bellman rank, Bellman eluded dimension. New rich classes of our problems, reinforcement problems, and sample efficient guarantees. Sample efficient algorithms. Sorry. Okay. So we're going to introduce the algorithm for this GORF. So you can also think this GORF is like a general function approximation version of Elena algorithm, which is for the linear function approximation, but with global optimism. So for episodes, we first initialize all the data set, D1 to DH, to be empty set, so that we don't have any data. And we have a confidence set, which is similar to Elena. This is the initial confidence set. Of the value function to be F, that is the entire function class. So for episode, K, from 1 to capital K, we do the following, that we will choose a policy pi k. This is the policy we're going to use to collect data. And this is the greedy policy of the fk, where fk will specify how we choose it. Fk is a function, value function, where this fk is chosen to be the argmax essentially the value function in this confidence set at k minus 1 step. Then maximize f s1 pi f s1. Okay. This is the Q value. Look at the first states, and if the first step taking the greedy policy of f, and we know this is essentially just the v1 s1. Essentially the v-value function, and look at the initial value. So this is very similar to Elena, basically the same as Elena. The first step is we're doing optimistic planning. That is, we only look at the initial value. Okay. This is like global optimism, and we choose the value function that maximizes the initial value within this confidence set. And we set our policy to be the greedy policy of that value function. And then we collect a trajectory. S1, A1, R1, till SHH, RH. SH plus 1. By following pi k. And augment data. DH is equal to the original data set and union with one new data set. So the first three steps is basically the same as the Elena algorithm, where we do the optimistic planning. We look at our confidence set, and we pick the value function that has highest value on the highest initial value, which is the principle of global optimism. And then we just execute the greedy policy induced by that value, and we collect the data. Okay. There's nothing new here. And the new part of this Golf algorithm is in the confidence set, where we notice in the Elena algorithm, the confidence set typically tunes very specially to this linear structure. It look at the least square weights, and we say weights need to be close to our estimate. So here, how are we going to construct a confidence set? So we're going to construct a confidence set as follows. We look at our confidence set will be all the value functions within the function class, so that the Bellman residue LD, H, FH, FH plus 1 is less or equal to the smallest loss F in FH, LD, F, FH plus 1, plus beta for all H. Where this LD is exactly the same definition as in the fitted correlation, the Bellman residual definition. Well, I will just roll again here. This LD plus 1 is defined as a summation over all the data A prime and fh plus 1 S prime A prime.
Professor?
Yes.
What's the meaning of inf on the right-hand side?
Oh, inf is the minimum. You can think this is just the minimum. If f is finite, you can replace it by the minimum. Inf is infimium.
Okay.
Okay. So I think the reason we constructed this kind of confidence set will be very clear if you still recall how we do the fit acceleration. Recall in the fit acceleration, basically we choose the value function fh hat to be the arc mean f in f of this LDH. Look at this Bellman residue square loss and f and fh plus 1 hat. Okay. This is precisely how we do the fitted correlation. So you can think if we don't have this plus beta or whatever the confidence set, if we only look at this inf f and this LD part, this is basically what we do for fitted correlation. For the Q duration, only look at the minimizer of this f, of this value function. If you only look at the value function that minimizes this Bellman residue. Well, in this like GORF or whatever the optimistic algorithm, we not only want a point estimator, which is like this fit correlation, we only look at the one value function. We want a confidence interval, a kind of like a confidence set. So this confidence set is constructed in this way so that we say, we not only want the fit correlation FQI estimator, which is the minimizer of this loss, we also will be okay with any function, value function, so that the loss can be slightly greater than the minimum loss. So you can think this is a slightly relaxation of FQI, so that FQI is a minimizer. That's great. But because there's some statistical error, my true value may not be the minimizer, maybe minimizer plus some like statistical slackness. So this is why plus beta is some slackness, and this is essentially a relaxation of FQI. Okay. So that's why this algorithm is, you can think this combination of FQI plus global optimism, because in the construction of the confidence set, its core is FQI. But we do some relaxation, and then we use the global optimism framework where we do the optimistic planning to look at the optimal, to look at the best value function that optimize over this like initial value within this confidence set. Okay, so this is the basic algorithm. Any questions about this confidence set or like why we want to do this algorithm? So here, beta is some statistical slackness. So I think the construction of the confidence set, basically, we want to guarantee that f star, that is the true value, true optimal value will always be in my confidence set, be k for any k, with high probability. So this is the reason why we want to do this like global optimism. Essentially, for whatever the optimistic algorithm, we always want the optimal value to be within my confidence set. So in order to do this, we were clear, like we cannot choose beta to be very, very small, because if beta is 0, then we're essentially reduced to FQI. And although we're doing FQI, but the optimal value may no longer be in this confidence set. So typically the choice of the beta is roughly something like constant times log the cardinality of F, and times like kh over delta, where k is the total episodes, h is the length of the MDP, and the delta is the probability. So something like that. And it needs to scale with the log cardinality of the function class F. Okay, so finally we will just introduce the guarantees for golf. Under a bunch of assumptions, under all the assumptions we have been talking about so far, the first is realizability. The second one is completeness. Those are two assumptions we talked in the last class. Completeness is basically says after applying the Bellman operator, it still remains in my function class F. Okay. So we only have just two assumptions. Then there exists a constant C. Such that if we choose, as we said, we choose this beta in this confidence set to be some constant times log cardinality of F times K times H over delta. Then with probability, at least 1 minus delta, we have the following regret bound. That is the regret up to capital K iteration, which is a summation of t from 1 to capital K. We look at the optimal value starting from S1 and subtracted the value of policy pi k at S1. This is upper bounded by O. Upper bounded by O, H, square root of dk beta, where this d is the Bellman rank of F. So this guarantee essentially says two things. I think it's first generic, very generic. It no longer depends on any states or actions. So this is the same as whatever the guarantee we want for the generic function approximation or like even linear function approximation. And most importantly, other than like this h horizon or some like small log factor, this guarantee essentially the regret only depends on two important quantity. One is the Bellman rank. We already said. Second one is this log f, log cardinality of the function class. So we already mentioned in the offline, we require two things. One, log f to be small. The other one, we have like concentrability coefficients, like all policy concentration or single policy concentration. Well, in the online setting, the single policy concentration is essentially replaced by the Bellman rank. This guarantee essentially says the natural algorithm, which this Golf algorithm, just combine the FQI with global optimism, will be able to find the optimal policy for any reinforcement learning as long as this reinforcement problem has a small Bellman rank. So this kind of says also Bellman rank is kind of like a natural notion because this natural algorithm is able to just solve any problem with small Bellman rank. Okay, any questions so far? I guess if no questions, so this essentially wrap up what do we want to talk about the general function approximation. I guess if you have any questions about function approximation, it's also a good time to ask now. And we will then proceed to the next topic of this course about the multi-agent reinforcement learning. So we roughly have 3 weeks left, or 3 weeks. And we will spend the remaining of the semester 2 weeks talking about multi-agent reinforcement learning, and 1 week talk about partially observable reinforcement learning. I think both topics are very exciting to me, and both topics are kind of like more advanced than those settings. So far, we have been only focusing on like a single agent fully observable scenario. That is, we use the model of Markov decision process. And in both multi-agent scenario and partially observable scenario, we'll use like more advanced models we'll introduce in this class. Okay. So multi-agent reinforcement learning. So in the multi-agent reinforcement learning, we're specifically talking about a bit overview. Like we're specifically talking about two models. That is normal form games, which you can essentially think this is like a counterpart of bandits in the multi-agent scenario. Like bandits is a more simple version of MDP without any state and transition. So normal form game is more like a basic version of the game we're gonna study in this class without any states and transition. So this is like the basic form of games. And then the counterparts of an Markov decision process would be Markov game. So this is the final thing we're gonna study in this class. That is essentially extending the MDP has this Markov structure to the gaming scenario. So the reason we want to understand the multi-agent reinforcement learning is in many applications in the real world. involves more than one agent. Like for example, if you play some video games or in some robotic scenario, there are multiple robots. They either want to like collaborate or compete with each other, and also like a lot of like military applications. And you can imagine, like for example, a lot of battleships, and they want to like cooperate with each other, and they have some strategy. So what is the major difference between like so I think one naive view of this multi-agent reinforcement learning is saying, why not we just directly reduce it to the single agent reinforcement problem, because I just treat all other agents as an environment. Then that seems like we're going back to the single agent scenario. Unfortunately, the answer is not that simple, because the major difference between the other agents and all we treat as an environment is so far in a single agent reinforcement learning problem, we always look at a static environment. That is, we assume environment always has the same transition probability. So we develop model-based algorithm, learn a transition, or we develop a value-based algorithm, which implicitly assume the environment is fixed. Environment will never change, and environment follow the same transition probability or same dynamics. Well, in the multi-agent scenario, one very important thing is the other agent is adaptive. So those agents can actually change their strategy across the game. And so they are no longer considered fixed. So that's why you cannot just blindly apply whatever we learn from single agent reinforcement learning and treat it as a fixed environment. Okay. So that's why we require a little bit more special treatment. We already said there are a lot of examples, including Go, StarCraft, which are the famous DeepMind examples that already beat the world champion, and also some robotics, and etc. A lot of other applications. And we also mentioned there are multiple different settings for multi-agent reinforcement learning. They are cooperative settings. Where all the agents trying to achieve the same goal, but there are also some competitive settings. Where essentially like StarCraft, where two players just want to compete and to win the game, like Go, StarCraft, all like competitive games. So in this lecture, we will first focus on the purely competitive setting. The reason is cooperative setting is more like a distributed setting of single agent reinforcement learning. So if you can collectively, like you have a centralized player which can essentially tell everyone what to do, it becomes more similar to a single agent problem. Well, in a competitive games, like this opponent being adaptive is like push it to the extreme. There are a lot of interesting game theoretical phenomena will happen in the competitive setting. So we'll first focus on the purely competitive setting. That is, we will focus on the basic setting of purely competitive game. That is the zero-sum game, two-player zero-sum games. And later, we will generalize it to like multiplayer general sum games, and how we're going to develop some concepts for that. So for this class, let's just focus on the two-player zero-sum games. So as we said, we first considered the basic form of games, normal form game, essentially games without state and transition. Which is the normal form game. So normal form game is quite simple if we consider normal form and two-player zero-sum game. Essentially, to define a normal form game, all we need is just a utility function. So we assume each player has an action set. Let's say A and B. So the first player may choose an action in A, and the second player chooses an action in B, or like a min player or max player. So we'll talk about that, the two-player. And the entire game is specified by a utility matrix. R in this a real number A times B, where A is number of action, B is number of A and B is number of action for each player. Where the entry RAB gives essentially this is a matrix, and we can look at one entry that is when the first player take action A and the second player take action B, gives the reward of, let's call the first player the max player, because we want to maximize this. And because it's a zero-sum game, the reward of one player is the loss of the other player. And so we just have one single matrix, and this matrix essentially specifies what's the gain of the max player, and because it's a zero sum, so it simultaneously also is the loss of the other player. By the way, I should also emphasize in this normal form game, we assume both players play simultaneously. Okay, so maybe I should not use the language, like first player, second player, should be like a one player, the other player, or the max player, the min player. So I think this abstract concept will be illustrated by one very simple example. Like we can look at the game rock, paper, scissors. So this is a perfect example of this normal form game because we can first like every player has both player has the same action set. Where action set essentially we have three actions that we will either choose rock, or choose paper, or choose scissors. And then the reward utility matrix can be written as the following. Because my action set has three actions, so the reward utility matrix is like 3 by 3 matrix, where each row and column corresponding to one action. So for example, the first action is rock. The second action is paper. The third action is scissors. Then we just write down the utility. Let's say the role player is the max player, so we will just write down the utility for the role player. So when the role player plays rock and the column player plays rock, we know this get 0 reward because it's a draw, and the same thing here. And if the role player plays paper and the column player plays rock, and we know the role player wins, so it got 1 utility, 1 reward. And otherwise, in this case of scissor and rock, it loses, so you get -1. So we can similarly fill out the entire reward matrix to be 1, -1, -1, 1, 1. So this specifies the game of rock, paper, scissors. Okay, since we're running out of time, I guess I will stop here. And we just basically introduce the form of normal form games. In the next lecture, we'll continue talking about what is solution concepts for the normal form games and how we're going to find it. And then we're going to move to the more general case of Markov games and develop solution concepts and planning and algorithms in that kind of scenario. Okay, thank you.